All right, so let us start with a recap. Okay, so what we have been discussing yesterday was in continuation with what is known as a predicate logic. Okay, and just to recall what is predicate logic, so the subdomain of logic which deals with predicates, or what we also known as propositional functions, is known as predicate logic. Okay, so what is this predicate or propositional function? A propositional function on a predicate is that kind of statement which is unambiguous till you put it in some context. Okay, so there is some property that you are trying to test, and there is some variable on which you try that property. So depending on what values this variable takes, the truth value of the statement is ambiguous. It can be either true or false depending on the value. Okay, so such kind of statements or such kind of functions are known as propositional functions or predicates. Now what we have been discussing in yesterday's lecture as well as in some previous lectures is how do we change a propositional function to a proposition. Okay, by which I mean that a statement which has unambiguous truth value, that is it will be either true or false. Okay, so there's no shade of doubt what is its truth value. Okay, and we discussed there are different ways to do it. Can you quickly summarize what are the two basic ways by which I can change a proportional function to a proposition? Yes, class. What are the two ways by which we can change any predicate or proportional function to a proposition? Excellent, Dhananjay. One of them is quantification. Okay, that is we apply some quantifiers in front of it, which will change our proportional function to propositions. And what is the simpler, more simpler version? Exactly. You specify the value of the variable. Okay, you fix the value of the variable, and based on that value, you check, whether the given property is satisfied or not, and that will give you whether it's true or false. Right. So second part is what we had discussed in depth yesterday. So in quantification, like the two popular quantifiers which are used in what you say the predicate logic are the universal quantification, which is denoted by this symbol inverted A, and you have existential quantification, which is denoted by an inverted E. So what are the idea behind universal and existential quantification? The universal quantification of a sentence is said to be true if the property is satisfied for all the elements in that domain. Okay, and if you recall, the universal quantification can also be written as, you can write it as a what you say, as a conjunction. Okay, a sequence of conjunctions of the elements in that domain. Okay, and by that I mean that if all of them are true, only then it is true. Okay, similarly the vice versa holds for existential quantifier. In existential quantifier, what we say is it should be true for at least one value in the domain. If it is true for just a one value, okay, it may be two, three, four, that doesn't matter, but at least one should be, uh, there should be one element in the domain of discourse for which this statement or property is true. Okay, and then we say the truth value of existential quantifier is true. Okay, and we can represent it by a disjunction, or what we say in common terminologies, or, which means if any one of them, any one of the values in the domain is true, then the entire statement is going to be true. Okay, so these were the two popular quantifiers we studied, universal and existential. In existential, there is a special case. Okay, a special case called a uniqueness quantifier. Okay, denoted by E exclamatory or E subscript 1. Okay, what does this denote now? Anyone recalls what does uniqueness one denote? It's a special case of existential quantifier. Okay, so what are the conditions, special conditions that it needs to meet if you have to have a uniqueness quantifier to be true? Yes, class, what are the special conditions for uniqueness one to be true? Very good, Tanya. It is that, so existential quantifier was that at least one of the elements should be there for which this property is true, right? But in this, there should be exactly one element, and that one element is your unique element for which this is true. Okay, if you have exactly one element for which the given property is true over the domain of discourse, then we say that the universal quantification, sorry, uniqueness quantification is true. Okay, and then we saw different examples of how you can have different quantifiers in between, like you can have sometimes exactly two, or say at least three, at most three. So you can have different variations. It's not just these three are the only ones, but the universal and existential are the standard ones, and all others lie in between. They are the two extremes of quantification. One more thing we had discussed yesterday was use of quantifiers in context of loops, right? So, what would be the stopping conditions if you want to check for these quantifiers, right? So, what we are going to discuss today, we are going to kind of wrap up around the predicate logic. We'll see some of the operations involving these quantifiers. Okay. So, any questions till the previous lecture, like till tomorrow's discussion? Sorry, yesterday's discussions. Any questions? Yes, class. Any questions? No. Yes. No. Okay, so I assume there are no questions. So let us then start with the topic for first topic for today, which is the precedence of quantifiers. Okay, so if you recall, when we had done various logical operations, we had discussed the precedence. Okay, now where does precedence come into the picture? If you have a compound statement, by compound statement I mean it involves a lot of different primitive logic statements, then you have different operators being involved. Okay, so the ambiguity arises, which one do you solve first? Their precedence of operators helps you to solve the problem. Okay, and if you recall, this was the precedence sequence given to various logical operators. The negation gets the highest preference, then you have disjunction, sorry, conjunction, then you have disjunction, then you have implication, then you have bidirectional implication. Okay, now if we bring the quantifiers into the same picture, the quantifiers, both universal and existential, have higher precedence than all logical operators. Okay, so in general, uh, the even below above negation you have your quantifiers. Okay, so you apply first quantifiers and then you apply all these operators. Okay, so we can see an example here. If we have for all x p of x or q of x, okay, so the way you visualize it is the disjunction of for all x p of x and qx, not like this p of x disjunction q of x and then for all x outside it. Okay, so for all x, or quantifier gets the first preference of evaluating, and then you apply it to the other operators. Okay, so this is the correct version of representing this statement rather than this. Okay, so quantifier gets first preference over the remaining operators. Okay, so this is quite useful when you have to kind of resolve the precedence in compound statements. Okay, so where is the precedence of quantifiers? It's at the top. You get to have quantifier statements higher precedence than the remaining operators. Okay. Okay. Now let us try to dig little bit deep into the quantifier statements. Like, how do we apply these quantifications? So far we were using these quantifiers on just single variables, right? Now, if they are in context of a statement, a compound statement, how do we kind of use them? Okay, so whenever a quantifier is used on some variable, okay, so suppose I write for all x p of x, so I am using a quantifier on variable x. So whenever you use a quantifier on any variable, in such a case we say that that variable is now bound. Okay, so any variable in a predicate, in a proportional function, in a predicate statement, if it is bound by a if it is used with a if a quantifier is used with it, such a variable occurrence is known as a bound occurrence. Okay, so and any occurrence of variable which is not bound by a quantifier, or there is no value given to it, you have not fixed its value, such a occurrence of variable is known as free. Okay, so in any predicate statement your variable can have two kinds of occurrences. It could be a bound variable, okay, which means a variable which has been bound by some quantification, or it could be a free variable. Free variable means neither you have applied a quantifier on it nor you have assigned it some value. It's free to take any value that it wants to take. Okay, and bound variable means you have either applied a quantifier to it or you have directly assigned a value. Okay, so these are the two types of variable occurrences that we normally encounter in predicate statements or proportional functions: bound occurrence and free occurrence. Okay, now before I go ahead, so let me just try to see whether you understand or not. So suppose I write a proportional statement, okay, which has say three bound variables. Okay, this is first scenario. Then I write a second proportional statement which has say two bound variables and one free variable. Okay, which one of them can give me a proposition? Can first one give me a proposition? So I had a proportional statement. I made in that statement there were three variables and all three of them I bound them. Okay, either by assigning quantification or by assigning values. Can I get a proposition out of it? Yes, no? The answer is yes, right? Because to change a proportional statement to proposition, what you require is either to assign some value or some quantification. But what about the second case, where I had again three variables, but two of them I bound either by quantification or by value, but one of them is free. Can I get a proposition out of it? Excellent. No. Why? Because no matter you have removed the ambiguity from the two variables, but one variable is still free, which may not give you the final value of the proposition or the compound statement. Okay. So this is something you need to keep in mind, that whenever you have free variables, it's not easy to get your proposition out of it unless you bind that as well. Okay, now let's turn back to it. Now all the variables that you normally see in a proportional function or a variable, if you want to change into proposition as we inferred from these two examples, what you need to do, you need to bound them. Okay, either you bound them using a quantifier or you fix their values. Until and unless you have all the variables which are bound or whose values are set, you can never change it into proposition. Okay, so how do you bind the variables or assign values? You can do as we studied using different quantifiers: universal, existential, or you can do value assignments, or you can even use other kind of quantifiers. So basic idea is, if you ever want to change the proportional function to proposition, all the variables should be bound or there should be some value assigned to them. If there is any, even a single free variable, you cannot change it into a proposition. Okay, so that's like the first key takeaway from this slide, that if ever you want to change a proportional function to proposition, key thing is there should be no free variables at all. Okay, okay, so now let us see the second part of it. Now when you look at a logical expression, okay, so suppose I write for all x p of x. Okay, so I have bound the variable x by universal quantifier. Okay, but the part of the logical expression to which I have applied the quantifier, that is known as scope of quantifier. Like in this statement, when I write for all x p of x is the scope of quantifier. Okay, or suppose if I have, suppose for all x p of x, let me just write it, or q of x. Okay, so can you tell me what is the scope of variable? What is the scope of this quantifier for all x? Okay, this will involve two ideas. One is the precedence of operators. Second is the idea of where do you apply the quantification. So if I have a single p of x, the scope of the quantifier is p of x. Scope means what part of logical expression do you apply this quantification. Okay, now if I write for all x p of x or q of x, okay, how do you first solve this? Do you do this or do you do this? first or second? Okay, so we just had seen this example, right? So when you have for all x p of x q of x, this is a disjunction of not p of x and q of x. Rather, you apply quantification on first one and then you do a disjunction, right? So second one is the correct one. Okay, unless you are given the parenthesis from on your own, then you can take that, right? But if there are no parentheses, then using the precedence of operators, it is actually a disjunction of first quantification of p of x and then q of x. Okay, which means what is the scope of this quantifier? What is the scope of the quantifier class? Is it p of x or q of x or just p of x? Very good, Dhananjay and Hasib. It's just p of x. Okay. So what does scope indicate? Scope indicate what is the part of your logical expression where you apply your quantification. Okay. So consequently, what you have is a variable is free if it is outside the scope of all quantifiers. Right. If you have a number of quantifiers applied and you have some variable which is outside the scope of all of them, such a variable is also known as free variable. Okay, so what is a free variable? A free variable is that variable which is outside the scope of all quantifiers in that state. Okay, so let us try to see it with the help of an example. Okay, so suppose, look at this example. There exists a x such that x plus y is equal to 1, right? So what are the bound and free variables in this case? Okay, so I have, there exists a x plus y is 1. Okay, tell me what are the bound variables, what are the free variables? So which one is a bound variable? So there are two variables, right? X and y. Which one is a bound variable? Excellent. X is a bound variable. Why? Because we have bounded using a quantifier, right? And what is the scope of existential quantifier? So is, first of all, is y bound or free? Y is free, right? So variable x is bound. By quantification there exists x, but y is free because it's not bound by any variable, nor we have assigned any value to it. Okay, so you can see in this statement x is bound and y is free, right? Now similarly, tell me in this context, there exists a x such that p of x, then you have and of q of x, then you take its or with for all x r of x. Okay, what are the free variables, what are the bound variables? Okay, so you can see the scope of there exists x, and for this for all x. Okay, so before you tell me what are free and bound, tell me what is the scope of there exists x? What is its scope? Scope means what part of logical statement is this condition applied. Okay, so luckily you already have parenthesis, right? So that's correct, Dhananjay. So scope of this existential quantifier is whatever is within the parenthesis, right? Similarly, what is the scope of universal quantifier? It is this r of x, right? Now remember the definition of free variable. Free variable is that variable which is outside the scope of all quantifiers. Okay, so you can see this x as well as this x is bound under this scope. Similarly, this x is bound under the universal quantifier. So are there any free variables? Are there any free variables? No, and all x variables are actually bound, right? So that was scope of the variable. What are free variables, what are bound variables? Okay, now let me just kind of rewrite it. Suppose I'll write there exists a x p of x q of x, or for all y r of y. Can I write it like this? Will it affect my statement anyhow? Can I do this renaming of variable? Will it affect my statement? Okay, so Abe says yes, Arpamit says no. Anyone else? Will it affect my statement? Just try to see the scope and then try to analyze. Okay, ultimately, when do I say that my statement has changed? If I give some truth values, its output should be changed, right? So, do you think by variable renaming in this case, is it going to affect my statement? Okay. Okay, so Abhay is also now on no. So actually, it's no, right? The reason behind this saying no, it will not affect is because the scope of variables is different. Okay, if the scope was say x, and it was suppose it was something like this: there exists a x, p of x, and of q of x for all uh, x r of x. Okay, and then if I change it to y, will then it affect it? If the scope of this x was also including r of x, will then it affect if I change the variable to y? It will, right? Because the scope was overlapping. But in this case, since the scope was disjoint, I can do variable renaming without having been affected. Is this clear, more or less? Like the three examples, the scope, then when I renamed the variable, and when I changed the proportion. Is this clear? Okay, so the main key takeaway here is, as long as your scopes are disjoint, you can rename variables because they are not dependent on each other. But as soon as their scopes start overlapping, you cannot do renaming, right? Now, that raises a question: have you seen it ever in programming, this concept being used, right? Have you ever seen this concept being used in programming ever when you did your C programming? So where whoever has got this idea, where have you seen this kind of idea? Excellent, Dhananjay. Okay, so that's why keep telling you, right? So discrete maths is not just maths; it's very dependent on computer science. This is where you use the idea, right? Whenever you have, suppose for loops, too many for loops, okay, and if they are independent of each other, you can actually use the same loop variable if they are not dependent. Same thing applies if you have a function inside and outside a function. So if you have a function inside it, the scope of that variable is local. So if you have a same named variable outside, you can just reuse it because their scope is different, right? So this is where we use this renaming part and scope part when we go into programming. If we have variables whose scope is different, right? Like I have defined my own function, and I use some local variable here. Okay, and I have a main function, and I use the same variable there. This will be allowed because their scope is different, right? But if you write same variable name inside the main function, two variables with same name, is this allowed? In normal programming, is it allowed to have say two variables of same name within same scope? Yes, class? It is not allowed, right? And the concept behind that is exactly of the binding variables. So the exact idea of binding variables and quantification gives the idea behind your programming idea of when you determine the scope of variables and whether you can rename variables or not. Okay, is this clear, class? Is this clear to everyone? See, all these things they're not on books, okay? So you need to infer them from the ideas you have. Okay? Is this clear to everyone? Okay, excellent. Okay, so let us move ahead now and let us try to see various logical equivalences which involve quantifiers. Okay, so for that, firstly, let's revisit back this term. What do we mean when we say two statements are logically equivalent? Okay, can anyone recall? What do we mean by it when we say two statements are logically equivalent to each other? What does it mean? How, or in other words, how do we prove that two statements are logically equivalent? Excellent, Rishita. It is, if you want to prove any two statements are logically equivalent, what you need to show is their truth tables are same. That is, whenever, no matter what value you give to the predicates, okay, but the within the domain of discourse, no matter what value you put for the predicates, the final truth value is going to be the same. Okay, if it is true, so you say the two statements are logically equivalent and you normally denote it by this statement. The statement S is equivalent to T by using these three parallel lines, right? So a simple quantification statement that you can see here is, if I apply a universal quantification on a conjunction of two operators, okay, so what we have is, we can apply the universal quantifier on both. Okay, so what kind of property is this? I have a property applied on a conjunction, and it can be applied on the individual components as well. What kind of property is this? Very good. It is a distributive property of quantification over the conjunction, right? So you can try for yourself. This is equivalent. The way you have to do it is, you need to make truth table of this, then apply the quantification, universal quantification, use different truth values, okay, all possible truth values over the domain discourse, and see if it is equivalent to this. Okay, all right. So moving on to the last aspect of the predicate logic, which is what happens if we negate the quantified statements. Okay, so let us try and start with some example. So consider this example that every student in your class has taken a course in calculus. Okay, so normally we see that predicate statements can be written in simple English. So I have this simple English statement. Every student in your class has taken a course in calculus, right? So we can see that it's like a universal quantification because it tells that every student is taking some course, right? So it's like a universal quantification statement where X is a student, and the property we are trying to look at is that X has taken a course in calculus. Okay, and what is the domain of discourse? Domain of discourse are all students in the class, right? Now, suppose I tell you what is the negation of this statement. You need to negate this statement. Can you write in like plain English what would be the negation of this statement? Yes, class. Okay, so let me try this one and then you can try for other. So if I write the negation of this statement, it can be written as, it's not the case that every student in your class has taken calculus. You know, it's not the case you every student, मतलब ऐसा नहीं है कि all of them have been involved in your calculus course. Okay, or in other words, what we are trying to point out is there is some student in your class who has not taken. Okay, you cannot be for sure that everyone has taken. Okay, so it's not like 100% revocation that nobody has taken. But if I say every student has taken, the opposite of it is there is some student who has not taken that course. Okay, when I say there is some student who has not taken that course, how can we write that in terms of quantifier? Yeah, so like Abhay has written, every student in your class has not taken. Okay, what does it mean every student has not taken? That means there exists some student who has not for sure taken your calculus course, right? So if you try to write it in terms of existential quantifier, so what you can write is there exists some student, okay, who has not taken your course, right? So P of X is taken a course. So we want to write that he has not taken a course. So I am taking a negation with P of X. But the main noteworthy point here is instead of every student, when you negate every statement, what it becomes is there exists. Okay. So if you want to hold a property for everyone, if you want to negate it, so how do you show a counter example? Okay. So if you recall, like, when do we say for all x is true? Right? When do we say for all x is true? or universal quantification is true? Yes, someone has raised the hand. You can unmute yourself. Sorry, I'm not able to see the raised hand screen. Just a minute. Somebody had raised the hand. Please unmute yourself. It's all right. Is it by mistake? Okay. Gotcha. Okay. So let's come back here. When I say for all x p of x is true, when do we say it's true? Right? When do we say it's true? When all the elements in the domain of its discourse are true. Right? Now, if I have to prove it's false, how do I prove a universal quantification is false? Yes, class, how do we prove? Recall we had summarized that table. How do we prove a universal quantification is false? Exactly. You try to find out one counter example for which it is false, and if it is false for one, we know that it's going to be false for everyone because universal quantification is actually a conjunction, right? So if I find even one of them is false, I can prove it's false. Okay, so that is what is the negation of the universal quantifier. If you are looking for all students or in your class satisfy some property, if you have to negate it, you need to just find one counter example. Okay, so that's why there exists some example for which this is not true. Okay, so that gives us our first negation property, that if I apply negation operator on for all x p of x or the universal quantification, what it will do, it will flip for all x into there exists x and the negation will go inside. Okay, so this is how we have for universal quantification. Okay, similarly, if I look at the other case, suppose I have there is a student in this class who has taken a course in calculus. Okay, so it's a there exists some student in the class who has taken this calculus course. Okay, now if I have to kind of negate it, okay, so what I mean is every student in this class has not taken a calculus. Okay, so again the same thing applies. If I have to apply show that there exists q of x is true, what do I need to prove? Remember, it is a disjunction. So if I have to prove that there exists or existential quantifier is true, what do I need to prove? Yes, class, do I need to prove all of them are true or at least one of them is true? Only one, at least one of them, right? So when I negate it, what I need to do is I need to show all of them. Now if I have to show they are false, I have to show it's false for all of them. Only then I can show that the given quantification has been negated. Okay, which gives us the second version of it, that if I take negation of there exists operator, the there exists gets flipped with for all x and negation goes inside. Okay, so have you ever seen this kind of thing happening before in set operations or in logical operations, that you have some form of complement or negation, it flips the things and goes inside? Have you seen it somewhere before in this course? Excellent, Ankita. De Morgan's law. Remember, if I have A union B complement, what is it equal to? You flip union to intersection and you take the complements inside, right? That's exactly what is being done here. You flip existential to universal and universal to existential, and you bring this knot inside. Okay, a much better way we'll just shortly see that why it's actually a version of De Morgan's law. Okay, I'll keep that a question mark for now, but we'll just see very easily why this is true. Okay, so let's just quickly summarize the negation statements or De Morgan's law for simple predicate logic. So if you have negation of existential quantifier, it is equivalent to taking universal quantifier of the negation of that predicate proportional function. Okay, so when will this negation be true? This negation will be true if for every x p of x is false. Okay, so opposite of what we would say for existential. Similarly, if you have the negation of a universal quantification, what it is equivalent to? Existential quantification of the negation of that proportional function. Okay, that means you consider the opposite. You need to show there exists an x for which p of x is false. Okay, and same vice versa applies when you have to prove that they are false. Okay, uh, is this clear? Is this clear, class? The De Morgan's law on the quantifiers. Huh? Okay, so let's now come to why we say that this is actually a De Morgan's law. Okay, now if you recall, when I say for all x p of x, what is an equivalent way to write it in terms of the logical operations? Yes, class. What is the logical equivalent of writing for all x p of x? Very good. It is the conjunction, right? We can write p of x1 and p of x2 and so on and so forth till p of xn. Okay. Now, when I apply negation to it, okay, apply negation to all of them. Okay. Now, we know that when I take negation of A intersection B intersection C and so on, what is the resultant? You can apply De Morgan's law and take the negation of all and you flip union to intersection and vice versa. Okay, same thing applies here. When negation goes inside, what it is going to do, negation will go to the individual elements and it will keep on flipping union to intersection and intersection to union. Okay, and what is this equivalent to? This is equivalent to disjunction of x not of p of x. Okay, and same thing applies for when you want to apply negation to quantification. That is the disjunction operator. So when you apply negation operator to each one of them, it keeps on flipping the conjunctions to disjunctions and taking the negations inside. Okay, so that's where you can see how it's actually just a generalized version of De Morgan's law. Okay, so let us try this example. So what are the negation of this statement? For all x, x square is strictly greater than x. Okay, so you need to apply negation operator to it and tell me what is the resultant statement. Okay, so you need to apply the De Morgan law and tell me what is the negation of this statement. Okay, do it step by step. First take negation inside, do the flipping, and then tell me the equivalent statement. Yes, class, be a little quick. I need to discuss the tutorial solution as well. Okay, so when negation goes inside, first thing you're going to do is it will become there exists, right? And negation will come outside this. So that's the first step, applying just the De Morgan's law, right? You negation goes inside, flips for all to there exists, and negation goes inside to the statement. Okay. Now, if you have to write negation of x square is greater than x, what is the negation of this statement? Okay, so I have x square is greater than x. What is the negation of this statement, class? What is the opposite of this statement? Less than or less than equal to? Yes. So it is x square is less than equal to, because you don't have to keep some gap. Okay, the exact complement of it. If x square is strictly greater than x, so negation of this is x square is less than equal to x, right? And that's exactly what is the negation of this statement. There exists a x such that x square is less than equal to x, right? Now try this example. What is the negation of this statement? There exists an x square is equal to 2. Okay, do again same step by step. Apply negation, flip the quantifiers, then apply negation on the inside statement. Excellent, Ankita. Okay, so if I apply negation to this, okay, so negation goes inside, it flips the quantifier, right? Now negation comes with the proposition. Now we know that negation of x square is equal to 2 is simply x square is not equal to 2, right? So this is what you have as your negation. Okay. Is this are the two examples clear? Are the two examples clear, class? Okay. So let me just move to the last topic and then we'll stop. The nested quantified statements. Okay. Now we have seen examples where we had one quantifier, but what if you have a nested quantifier? Nested means you have a number of quantifiers applied together and then you have to negate. Okay. So one version we saw there was compound statement and then you had to negate. So we knew that you need to flip the operators and put negation with the individual components. Now the question is, what if you have nested quantifiers itself? Okay, how do you solve them? So whenever you have quantified statements with more than one variable, which is negated successively by applying De Morgan's law. Okay, so what you need to do is whenever you have nested quantified statements, what you need to do is you need to apply De Morgan's law successively. That is, whenever what you're going to do, the negation which is in front, you're going to pass it forward, and as and when it's moving forward, if there is a for all, it changes to there exists. If there is a there exists, it's changed to for all, and you keep on passing the negation symbol towards the inner loop from left to right. Okay, so it is like if I have a negation and I have for all x there exists a x, I'm going to pass on this from left to right, and whenever it hits a quantifier it will flip them and it will try to push in the negation towards inside, towards these compound state. Okay, so let's try this example. So I have three variables. I have a three array predicate variable p of x y z, and there are three nested quantifiers. Can you tell me what will be the resultant of this? What is the equivalent statement for this? Apply the same rule. Move negation symbol left to right, and when it encounters a quantifier just flip them up. Okay, can you tell me where would it stop? What would be the equivalent statement? Okay, others also please try. Very simple. You just have to pass on the negation symbol to the inside from left to right. And whenever it encounters a quantifier, you have to just flip it. Okay, great. Okay, so exactly that's what is the answer. When not goes inside, it flips for all to there exists. Then it moves to there exists, it flips it to for all. Then it again moves to there exists, it flips it to for all. And then finally, this negation is pushed onto the proportion. Okay, so normally we don't do it step by step like you have seen here. Now you know the rule, so you can directly apply it straight up. Okay, is this clear, class? So I'll stop there. We'll discuss the tutorial solutions. Any questions till this point? Any questions till this point, class? Class here, yes or no? Okay, so I'll stop it here.